Picture this, a universe condensed into a point smaller than an atom. This tiny speck held all the matter and energy we see today. Then, about 13.8 billion years ago, this speck exploded. This explosion, called the Big Bang, marked the beginning of time and space as we know them. From this fiery birth, the universe rapidly expanded and cooled, setting the stage for the formation of galaxies, stars, and planets. The Big Bang wasn't just an explosion in space, it was the expansion of space itself. Imagine baking a loaf of raisin bread. As the bread rises, the raisins within it move farther apart. Similarly, galaxies in our universe are moving away from each other due to the expansion of space. The evidence for the Big Bang comes from various observations. One key piece is the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates the universe. Think of it as the fading heat from a dying fire. This radiation tells us about the conditions in the early universe and supports the Big Bang theory. Understanding the Big Bang is crucial to comprehending the universe's ultimate fate. The universe's beginning holds clues about its possible endings, and scientists continue to study the Big Bang's remnants to piece together the story of our cosmic origins. The universe is not static, it's a dynamic and ever-evolving place. Since the Big Bang, the universe has been expanding, and this expansion is not slowing down. In fact, it's accelerating. This means that galaxies are moving away from each other at an ever-increasing rate. Driving this accelerated expansion is a mysterious force called dark energy. Dark energy is thought to make up about 70% of the universe's total energy density, and its nature remains one of the biggest mysteries in modern cosmology. Imagine a balloon with weights attached to its surface. Gravity pulls the weights inward, just like it pulls galaxies together. But if you inflate the balloon rapidly, the surface stretches, pushing the weights further apart. Dark energy acts like the air inflating the balloon, counteracting the inward pull of gravity, and causing the universe's expansion to speed up. Dark energy's influence on the universe's expansion has profound implications for its ultimate fate. Depending on how dark energy behaves in the future, it could lead to various scenarios for the universe's end, ranging from a slow fade to a violent rip. Understanding dark energy is crucial for predicting the universe's long-term destiny. Scientists are currently engaged in extensive research to unravel the mysteries of dark energy. They are trying to determine its properties and how it interacts with other components of the universe. This research will provide valuable insights into the future evolution of the cosmos. Imagine a universe where galaxies drift farther and farther apart, becoming increasingly isolated islands in the vast cosmic ocean. Stars, the building blocks of galaxies, eventually run out of fuel and die. Some collapse into white dwarfs or neutron stars, while the most massive ones collapse into black holes. This is the bleak picture painted by the Big Freeze scenario, one possible ending for our universe. In this scenario, the universe continues to expand indefinitely, driven by the relentless push of dark energy. As the universe expands, its average temperature drops. Think of a cup of hot coffee cooling down as it spreads over a larger surface area. Similarly, the energy density of the universe decreases as it expands, leading to a gradual cooling. Over immense periods, even black holes will evaporate through a process called Hawking radiation. Eventually, the universe reaches a state of maximum entropy, where everything is evenly distributed, and no more useful energy can be extracted. The universe becomes a cold, dark, and desolate place, devoid of light and life. The Big Freeze scenario represents a slow and gradual demise for the universe, a whimper rather than a bang. It's a fate where the universe simply fades away into darkness and silence. In contrast to the slow fade of the Big Freeze, the Big Crunch offers a more dramatic ending to the universe's story. Imagine the universe's expansion gradually slowing down, like a ball thrown upwards, eventually succumbing to gravity's pull. This slowdown could occur if the density of matter and energy in the universe is high enough to overcome the outward push of dark energy. As the expansion halts, gravity takes over, pulling everything back together. Galaxies, once drifting apart, begin to collide and merge, creating a cosmic dance of destruction. The universe contracts, and temperatures rise dramatically as everything gets squeezed into a smaller and smaller volume. This relentless contraction culminates in a singularity, a point of infinite density and temperature. This singularity resembles the one from which the universe is thought to have originated in the Big Bang, leading to the idea of a cyclic universe. In this model, the Big Crunch is not the end but rather a new beginning, giving rise to another cycle of expansion and contraction. While the Big Crunch presents a more dramatic and conclusive end than the Big Freeze, current evidence suggests that it's less likely. However, it remains a fascinating possibility and a testament to the cyclical nature often found in the cosmos. Section 5. A universe torn apart. The dreaded Big Rip. Imagine, if you will, a universe where the very fabric of space-time is ripped apart, tearing galaxies, stars, and even atoms asunder. This cataclysmic scenario is known as the Big Rip, a hypothetical end to the universe driven by the relentless and ever-increasing strength of dark energy. In this scenario, dark energy's influence grows over time, becoming so dominant that it overwhelms all other forces, including gravity. The expansion of the universe accelerates at an exponential rate, stretching space-time at an alarming pace. The first victims of this cosmic rip are large-scale structures like galaxy clusters. As dark energy's pull strengthens, these clusters are torn apart, scattering galaxies into the void. Eventually, even individual galaxies are unable to withstand the immense tension, and they too are shredded. As the Big Rip progresses, the destructive power of dark energy reaches smaller and smaller scales. Stars are torn from their galaxies, planets are ripped from their stars, and even atoms themselves are disintegrated. The universe ends not with a whimper or a bang, but with a cataclysmic shredding of existence itself. The Big Rip is considered a more speculative scenario than the Big Freeze or Big Crunch. However, it highlights the profound implications of dark energy's dominance and the potential for unexpected consequences in the far future of the universe. Section 6. The Final Curtain, Heat, Death, and the End of Energy. Imagine a universe where everything is evenly distributed, where there are no more stars, no more galaxies, and no more sources of energy. This is the state of heat death, a scenario closely related to the Big Freeze but with a focus on the concept of entropy. Entropy is a measure of disorder or randomness in a system. The more entropy a system has, the less organized and more uniform it is. The second law of thermodynamics states that entropy always increases over time in a closed system. In the heat-death scenario, the universe continues to expand, becoming increasingly cold and diffuse. Over vast periods, all matter and energy become evenly distributed, reaching a state of maximum entropy. Stars exhaust their fuel, black holes evaporate, and even the faintest temperature differences disappear. With no temperature gradients or energy differences, no work can be done, no new stars can form, no life can exist, and the universe becomes a stagnant and unchanging void. It's a state of ultimate equilibrium, where nothing ever happens. Heat death represents a fate where the universe doesn't end with a bang but with a whimper of sorts. It's not a destructive end but rather a state of ultimate stillness and inactivity. Section 7. Mysteries of the Cosmos, Unraveling Dark Energy. One of the most significant unknowns in our quest to understand the universe's fate is the nature of dark energy. This enigmatic force, responsible for the universe's accelerated expansion, remains shrouded in mystery. Scientists are diligently working to unravel its secrets, hoping to gain insights into its properties and long-term behavior. One of the biggest questions surrounding dark energy is whether it's a constant force or if its strength changes over time. If it remains constant, the universe will likely continue to expand indefinitely, leading to scenarios like the Big Freeze or heat death. However, if dark energy's strength increases, it could result in more dramatic endings like the Big Rip. Another area of active research is the relationship between dark energy and other fundamental forces in the universe. Understanding how dark energy interacts with gravity and other forces is crucial for predicting the universe's long-term evolution. Unraveling the mysteries of dark energy is one of the most significant challenges in modern cosmology. The answers we find will not only shed light on the universe's ultimate fate, but will also deepen our understanding of the fundamental laws governing the cosmos. Section 8. Which future awaits? The current scientific consensus. Given our current understanding of the universe, which of these scenarios is most likely to occur? Based on observations of the universe's expansion rate and the properties of dark energy, the current scientific consensus leans towards the big freeze or heat death scenarios. The evidence suggests that the universe's expansion is not slowing down, but is instead accelerating, driven by the relentless push of dark energy. If dark energy remains constant or its strength increases, the universe will likely continue to expand indefinitely. However, it's important to emphasize that our understanding of dark energy is still incomplete. We don't know for certain whether its strength will remain constant, increase, or even decrease in the future. Unexpected discoveries or changes in our understanding of fundamental physics could drastically alter our predictions. Section 9. Keep exploring, a universe of wonders. The quest to understand the universe's end is a journey into the unknown. While we may not have all the answers yet, the pursuit of knowledge and the exploration of the cosmos are endeavors worthy of our time and effort. The universe is a vast and mysterious place, full of wonders waiting to be discovered. By studying the cosmos, we gain a deeper appreciation for our place in the grand scheme of things and the incredible forces that shape our existence. As we continue to explore and unravel the mysteries of the universe, we should do so with a sense of wonder and curiosity. The universe is a treasure trove of knowledge, and each new discovery brings us closer to understanding our place within it.